Good morning everyone. Next section we have to see vector space and the topics are vector space, subspace, linear independent and dependent, basic and dimension, null space and column space and dimension theorem. First definition of vector space. A vector space V over a field F consists of a set of on which two operations addition multiplication are defined, so that for each pair of element xy belongs to V, there is a unique element x plus y belongs to V, and for each element alpha in F and each element x in V, there is a unique element ax in V, such that the following conditions are held. That means vector space means V is a vector space over the field F and it satisfies the condition addition and multiplication also. Addition means x plus y belongs to V and multiplication means xy belongs to V. It satisfies the following conditions. First property is commutative law. That means for all xy belongs to V such that x plus y is equal to y plus x in addition. Next one is additive associative law. For all xy z belongs to V such that x plus y plus z is equal to x plus y plus z. And for all x belongs to V and 0 belongs to V such that x plus 0 is equal to x and 0 plus x is equal to x. It's additive identity. Then next one is x comma minus x belongs to V such that x plus minus x is equal to 0 and minus x plus x is equal to 0. It's called additive inverse. And next property is for all x belongs to V and 1 belongs to V such that 1 dot x is equal to x and x dot 1 is equal to x. It's called multiplication identity property. And the next one is for all AB belongs to F and x belongs to V such that AB of x is equal to A into BX. And also xy of z is equal to x into y. It's called multiplication associative. And for all A belongs to F and x belongs to x and y belongs to V such that A into x plus y is equal to AX plus AY. It's called left distribution law. And the next one is right distribution law. That is for all AB belongs to F and x belongs to V such that A plus B of x is equal to AX plus B. These 8 conditions are satisfied. It's called vector space. In first theorem, let V be the set of all maximum matrix M cross N matrix with real entries. Let F be a rational or real number and it's defined A plus B into Ij is defined by Aij plus Bij for all A comma B belongs to M cross N and C belongs to F. Also Ca of Ij is equal to Caij. Prove that V is a vector space. V is a vector space satisfies 8 conditions. First A is defined by Aij, small aij, and B is defined by small bij, capital C is defined by small cij. And first condition is commutative property. Xy belongs to F, x plus y is equal to y plus x to prove. So here A and B are variables. A, B belongs to F, A plus B is equal to B plus A. A is defined by Aij and B is defined by Bij. So we add Aij plus Bij F M cross N. It's addition, so interchange the Aij and Bij, we get Bij plus Aij of M cross N. So it's separate Bij of M cross N plus Aij of M cross N is equal to A plus B is equal to B plus A. And next condition we have to prove x plus y plus z is equal to x plus y plus z. So we have to prove A plus B plus C is equal to A is Aij M cross N plus B is Bij and C is defined by Cij. So Aij plus Bij plus Cij. Take Aij outside, we get Aij plus Bij Cij. So it's defined by capital A plus B plus C. And the next condition, A belongs to V, 0 belongs to V. So we prove A plus 0 is equal to 0 and 0 plus A is equal to 0 plus A is equal to A. So A plus 0 is equal to Aij M cross N and 0 is defined by 0 Ij M cross N. So capital A is Aij M cross N. So A plus 0 is equal to A. Similarly 0 plus A is equal to A. And next condition we have to prove inverse property. So a comma minus a belongs to V such that a plus minus a equal to 0. So a plus of minus a is equal to aij m cross n, and minus a is defined by minus aij m cross n. So aij minus aij we get 0. So a plus minus a is equal to 0, and similarly minus a plus a is equal to 0. And next property is identity. A and 1 belongs to V such that a dot 1 is equal to a. So a dot 1 is equal to aij m cross n, and 1 is defined by 1ij, a into 1 a. So aij of m cross n, capital aij is defined by capital A. So a dot 1 is equal to a, 1 dot is equal to a. And next condition we have to prove a b c belongs to V. A dot b of c is equal to a into bc. So AB of C is equal to A is defined by Aij and B is defined by Bij is equal to Cij. So combine all those things and take outside Aij, Aj m cross n is equal to Bij and Cij. So Aij of m cross n is equal to Bij, Cij of m cross n. So AB of C is equal to A into BC. And next condition we have to prove C belongs to F such that A of B plus C is equal to AB plus AC. So A of B plus C is equal to A is defined by Aij m cross n and Bij m cross n plus Cij m cross n. So multiply Aij. So Aij Bij plus Aij Cij. So combine all those things. Separate Aij Bij plus Aij Cij. So A of B plus C is equal to AB plus AC. Next condition we have to prove A, B, C belongs to F such that A plus B of C is equal to AC plus BC. So A plus B of C is equal to Aij plus Bij into Cij. So Aij into Cij, multiply Cij plus Bij into Cij. So we get A plus B C is equal to AC plus BC. The above result set of all m cross n are real entities over the field F is a vector space. So the 8 conditions are satisfied, so it's called vector space. Next condition, prove that set of all polynomials T is a vector series. A is equal to A is defined by a0 plus a1x plus a2x square plus a3x cube plus etc. And B is defined by b0 plus b1y plus b2y square plus b3y cube plus etc. And C is defined by C is equal to c0 plus c1z plus c2z square plus c3z cube plus etc. So we have to prove the 8 conditions. First condition is commutative law. A plus B is equal to B plus A. So A is defined by a0x plus a1x plus a2x square plus a3x cube plus etc. And B is defined by b0 plus b1y plus b2y square. So interchange the addition. So we get A plus B is equal to B plus A. And next condition 2, x plus y plus z is equal to x plus y plus z. So we have to prove A plus B plus C is equal to A plus B plus C. So A plus B plus C, A is defined by a0 a1x a2x square plus a3x cube plus b0 plus b1x plus b2y square plus c0 c1z c2z square plus c3z cube. So we combine all those things, we get A plus B plus C is equal to A plus B plus C. And also addition, A plus 0 is equal to A, 0 plus A is equal to 0. And next condition inverse. Next condition identity. And next condition AB of C is equal to A into BC. And it's very easy problem. You do yourself. Next theorem. Let B be the vector space over a field F. And non-empty vector space W is called a subspace of V. If W1, W2 belongs to V and alpha, beta belongs to R, implies that which is alpha W1 and beta W2 belongs to W. We have to prove W is equal to A 0, 0 and A belongs to F is a subspace of R cube. So given W1 is equal to A, 0, 0 and W2 is B, 0, 0. So W1, W2 belongs to F. F is a field. To prove W is a subspace of R cube. So alpha of W1 plus beta of W2 belongs to W. So alpha of W1 is alpha into W1 is A, 0, 0 plus beta into B, 0, 0. Multiply alpha and beta inside. So we get alpha A, 0, 0 plus beta B, 0, 0. So separate alpha A, beta B plus 0, 0. So alpha W1 plus beta W2 belongs to W. So W is a subspace of R cube. Next theorem, prove that the intersection of two subspace of a vector space is a subspace of V. Let us consider V1, V2 are two subspaces. A and B belongs to V1 and A comma B belongs to V. To prove V1 intersection V2 is a subspace of V by using subspace definition, for all W1, W2 belongs to W and alpha, beta belongs to W such that alpha of W1 plus beta of W2 belongs to W. It's called subspace definition. So we have to prove V1, V2 belongs to V and alpha, beta belongs to F such that alpha of V1 plus beta of V2 belongs to V1 intersection V2. And alpha, beta belongs to V1, alpha A and A comma B belongs to V. Hence V1 is a subspace of alpha A plus beta B belongs to V1 and V2 is a subspace of alpha A plus beta B belongs to V2. So from equation 1 and 2, alpha A plus beta B belongs to V1 and intersection V2. Hence V1 intersection V2 is a subspace of V. Next condition is prove that the union of two subspace of a vector space need not be a subspace. So intersection of two subspaces must be a subspace, but union of two subspaces need not be a subspace. Let's consider A is equal to A comma 0 comma 0 and B is equal to 0 comma B comma 0. Here since A and B belongs to R cube, take A is equal to B is equal to 1, substitute in A and B condition, we get 1 comma 0 comma 0 belongs to capital A, 0 comma 1 comma 0 belongs to B. So here the union of the vector space is need not be belongs to A belongs to B. Hence A union B is not a subspace of R cube. Thank you for all. Next class we have to see the definition of subspace, another definition. Thank you.